This is a very brief explanation of paging, a system used in virtual memory systems for non-contiguous file allocation. You'll learn the theory for these questions under OS, but for now, let's get into the basic problems you may encounter. Very basically, the concept is this. Whenever the available space on the primary memory is insufficient, the system relies on assigning a certain space of the secondary memory to act as a virtual primary memory. Okay, so both memories are divided into equal chunks. Those chunks are named frames in the primary memory and pages in the secondary memory. Now the program can be loaded completely onto the pages of the larger secondary memory, and the primary memory can grab the pages it needs to process and loads them into frames for processing. The computer keeps track of each frame and each page using a bit sequence called addresses. Frames are assigned physical addresses, and pages are assigned logical addresses. Later on, you'll learn about how processors keep track of what is loaded into each page by keeping a separate page table to assist in mapping. Physical address and logical address are, as mentioned, a bit sequence. The number of bits used varies. This is known as the address bus width. While physical addresses are generated by the CPU, pages are a bit more complicated. There could be a large amount of pages, and each page contains a specific part of a process called words. So the address is split to represent these quantities into a few bits. So page and frame number can be represented by, in this case, 5 bits, and the rest of them will represent the offset. Now, what part of the word to be loaded? Often we'll be asked to find the number of pages or words. For that, you need to know a bit of binary math. Possible combinations of a bit sequence depend on the number of bits. Right? For example, a 2-bit sequence can have 2 to the power 2 or 4 combinations, and 3 bits can have 2 to the power 3 or 8 combinations. So you can find the number of possible combinations by raising 2 to the power of however many bits are used. So, if you wanted to find the total number of addresses, also known as the address space, in this case you would have to raise 2 to the power 16, since 16 bits are used here. Similarly, you can find the total number of displacements and pages depending on the amount of bits used for each quantity. In this case, that would be 2 to the power 5 pages and 2 to the power 11 offsets. So now that we have addresses to reference each frame and page, we can store data in them. The amount of data you can store depends on the system. For example, if 1 bit can be addressed, then the system is 1 bit addressable. If 1 byte can be addressed, then the system is 1 byte addressable. Imagine this to be a byte addressable system. Now we can store 1 byte or 8 bits of data per address. Let's say each address is 16 bits. So let's work out the total capacity of memory that can be used by this computer. The physical address space, or total addresses, is 2 to the power 16, right? And each address stores 1 byte or 8 bits. So simple math. The total capacity would be 2 to the power 16 bytes, or 32 kilobytes. Then this computer can only use a maximum of 32 kilobytes of memory, since the address bus width would not allow any more addresses to store more data. Make sense? So what about actually accessing virtual addresses? For each process, a page table exists to connect the frames and pages. So let's look at how this is implemented in the following scenario example. If we wanted to access the virtual address number 13, putting the page table aside for the moment, let's locate the virtual address 13. If you consider how each page has 4 words, you'll notice how the first page contains 0 through 3, the second contains from 4, the third contains from 8, and so on. Then the third page must have 13 within its range. So we've identified the page, then what is its offset? So if the first address in the fourth page is 12, we have to move 1 further to get to 13. So then the offset would be 1. That would be the difference between the first and the address that we need to get to. So you can work that out. Since there are 8 pages with 4 spaces, then the logical address space is 32 or 2 to the power 5, right? That means 5 bits are used to represent the offset. So the logical address that we're after is page 4, offset 00001. Okay. And if you ever ask the logical address, just combine the page number in binary with the offset. So Now we can use the page table to find what frame to load it into. The table has mapped page 4 to frame 10. So now all we have to do is combine the two to get our physical address, with 2 bits to show the frame and the other 5 representing offset. For all this complex theory, most problems you get are comparatively easier. Just take note to use these basic ideas and think it through. One easy example is the following question. If a computer system is byte addressable and uses 32-bit addresses to access any byte in its memory, what is the maximum usable size of its memory in gigabytes? Show all your workings clearly. So, what do we know? It's byte addressable, and one address can contain 32 bits. Then the address space would be 2 to the power 32, or 1 byte into 2 to the power 32 addresses. So take care for the conversions between bytes into bits, because the 8 bits could be confusing, but somehow the maximum usable size would be 4 gigabytes. So the next question, the memory of a computer system is byte addressable and has a maximum usable size of 4 gigabytes. What is the minimum width of its address bus in bits? So now we've got a different question. So what we know is that it's byte addressable, and we know the total capacity, but we don't know its address bus width. So we have to work backwards. So the address space would be 2 to the power x, x being some number of bits in the address. Okay. So that's the answer that we have to find. The total capacity then, would be 2 to the power x addresses into 1 byte. That gives us an equation that you can compare and get x in the indices. Now, the conversion here has the answer in the index. Now, mathematics can give you the answer by using log, but basically, if you can just remember how, if the index of both sides are equal, then the power should also be equal. Then that gives you the answer. X is 32 bits. And really, as far as paging calculations are concerned, that's really all there is to it. They'll give complicated problems with tables and stuff, but these principles are always the answer. So just keep that in mind. Good luck.